Just to set the context again, we had two very nice talks by Jeff and Shin. And here I want to talk about embodiment and how that works in the context of computing systems. The notion of embodiment is something that has roots in psychology and philosophy, and more recently in neuroscience and robotics. The idea that if you take cognition, it doesn't make sense unless it's actually embodied in an environment where it can make actions and learn about itself in the environment. So to do that, I want to focus on two specific things that I think are important from the perspective of how you might apply these concepts in computing systems. And so to do that, let's take a look at the notion of reflex versus reflect. So in many engineered systems, we have control loops that monitor inputs and effect actions. And these are very similar to what you see from neurobiology in terms of the autonomic nervous system that reflexively reacts to external inputs. And these actions are solely driven on external feedback. On the other hand, you might look at what Jeff talked about in terms of the abstraction and the hierarchy that he described, where you might want to look at reflection and introspection as models that consider not only past, but also potential future outcomes, so that you can engage in tasks such as planning, strategies, policies, and so forth. And these two systems, the fast and the slow, as we all know, work in concert with each other in biological systems, and we'd like to embody those ideas in computing systems as well. So to take a look at this, let's take a look at what this means in a simple computing system model. And we'll first start with looking at cyber-physical systems. Now, the idea of a cyber-physical system is inherently embodiment in the environment, because you have a computing system that is sensing things in the environment and then actuating back in the environment. And therefore, self-monitoring is very important because you need to be able to monitor where it is. So if you look at this picture here, it's a cartoon that shows a system. This colorful box here is a system which is monitoring itself. And based on some actions, it can generate simple adaptations so that it can go back and then react to external inputs, as well as possibly internal inputs. And these are done in the context of trying to manage a set of goals or a certain quality that one wants to achieve. And so this is something that we see today in most engineered systems in terms of feedback control. And there may be very sophisticated models of feedback control as well. Now, if we move forward, where does self-awareness play a role? The idea, again, is that you can allow for dynamic adaptation and resilience and autonomy. To understand that, you might look at the idea of creating a digital twin or a self-model of the system, which then can allow us to reason about potential future actions, about the possibility of planning, and so forth. So in this picture, if you look at the red arcs here, they actually generate a self-model, which is a digital twin of your existing system. And using that self-model, you can actually do self-aware adaptations. This incorporates the notions of reflection and introspection, which allows the system to do more creative planning and proactive actions so that the system can perform and deliver these types of goals and the quality that you desire in the face of changing environments. So that's the notion of this idea of self-monitoring as well as self-modeling. So following on what Shin talked about, I'd like to present something that we have, this very busy picture that we have in our article in the special issue. And it's so busy that your mind might spin, but let's take a quick look at this. What you see here is a system where you have a lot of sensors in yellow that allow a system to sort of monitor both the internal aspects, which you call the inspection, as well as the external aspects. And then we have some engines that assess the state of the system, that keep track of the goal of the system, and allow us to make decisions and eventually actuate. So the brown nodes that you see here are the actuation. And to do that, what we really need in this kind of a model is this notion of both self-inspection and environmental inspection, which relate back to the ideas that Chin talked about. But in doing so, if you zoom into one of these boxes, you see that there's a need for self-monitoring in this case, which requires both a static model of oneself as well as a dynamic model of the self. So in the introduction, we had Bernard talk about how a system needs to be initialized. So when we start with the system, we might have a very static model of what the system is. And as we proceed executing the system, we might have to adapt and build a dynamic model. And to do that, we need some history of where we've been and how we might move forward. And all of this, of course, requires this element of learning that you'll see as we go through this entire slide. The same thing can be replicated for the environmental modeling part, where you have, again, some environmental modeling, both a static and dynamic model, as well as a history. Having been able to inspect the system state and oneself, we can then get into assessing what we need to do. And the assessment is supported by this notion of goals. You may have a hierarchy of goals, you may have conflicting goals, and this goal hierarchy allows the system to decide how to transition between different goals and do the trade-offs that we heard about earlier. Once that's done, then you're in the position to make a decision in terms of what you want to actuate, and that's done with action control. So these different components are embodied in computing systems at very different levels, depending on the context of use and where it's applied. So you can see that if you look at a cyber-physical system today, it's inherently embodied in the environment. And we saw that in terms of examples in robotics. And you'll see in the special issue, there are articles that talk about unmanned vehicles and large-scale cyber-physical systems. But these self-awareness capabilities vary quite widely. The engines that we saw earlier in terms of how they self-assess, how they manage goals, what kinds of decisions they make, the actions that they do, and specifically the kinds of learning that they do are quite varying. On the other hand, if you look at computing systems and simpler IoT contexts, traditionally, there's been very, very little embodiment and self-awareness applied. But I would postulate that there's increasing need in the face of many of the constraints that we face today. These include long life, the ability to be resilient to various types of external influences, managing energy, security, et cetera. So if you read our IEEE article, you'll see showcases of different applications where these ideas have been applied for systems on chip, in the context of health monitoring systems for healthcare, and in terms of industrial control. So let me wrap up by talking about some of the open challenges that I see in terms of how we might apply these for computing systems. This is not an exhaustive list, and the special issue has many, many others, but I want to focus on some that we have explained in our article. The first is this idea of understanding the situation and reasoning about the situation. And so typically, this is what people refer to as situational awareness and reasoning. And it's a very complex concept because the situations change and the world model that you have may be static, but it can change very dynamically. So this is an extremely challenging issue in terms of how you can handle that. The second is the notion that we need to be able to take that static self model that was built at the time of initialization and evolve that at runtime depending on experiences that the system has seen. And so that would require automated runtime abstraction for enhancing and building the self model. And then, of course, learning is something you saw in all aspects of the self-awareness. So, how can we do dynamic learning in the face of yet unseen scenarios is a big challenge. And finally, the notion of adaptive goal formation and management. Many engineered systems we saw earlier are continually faced with doing trade-offs where you have some overall goal, but the trade-off might require you to change the goal and decide on doing planning in a different manner. So with that, I'd like to stop and hand back to our organizers.